Welcome SYBsc physics student. I am VP Devri, Department of Physics, Universe Commerce Science College, Ch1, District Ahmednagar. SYBsc Physics Semester 4th, Paper 1st, Oscillation, Waves and Sound. Chapter 1, Undamped Pre-Oscillation. And today's topic is energy of the simple harmonic motion. So in this topic here we studied some characteristics, and here this energy of the simple harmonic motion is one of the characteristics of the linear SHM. So the particle performing SHM is subjected to an action of restoring force, so its energy can be both here this kinetic and potential. Kinetic and the potential, and here by virtue of its motion it will have kinetic energy, and by virtue of the position it will have potential energy. So for the undamped SHM, the law of the conservation of the mechanical energy is valid, and we have the displacement, and that displacement are xt is equal to a sine omega t plus phi, then x is equal to dx by dt, and that is equal to a omega cos of omega t plus phi, and here x is equal to d square x by dt square, and that is equal to minus a omega square cos sine omega t plus phi, omega t plus phi. So here these xt is equal to a sine omega t plus phi, so that is it is equal to the displacement. This is the displacement. Now here x is equal to dx by dt a omega cos omega t plus phi, and that is the nothing but the velocity, and here these x d square x of dt square is equal to minus a omega square sine omega t plus phi, and that is equal to the acceleration. So here the graphical representation of the displacement, velocity and the acceleration, and when here phi is equal to 0, and it is shown in the particular diagram here. So here this is the diagram for this. So this figure represents the graphical representation of the displacement, velocity and the acceleration. Graphical representation of the displacement, velocity and the acceleration. So here these waves here we take this is the pi, then this is 2 pi, then here this pi, and here this is the 2 pi, here it is pi, and in this case it is a 2 pi. So here this is a graphical representation, plus a minus a omega minus a omega, and a omega square minus a omega square. So here this is the omega t, and here this figure first figure, which is represent as the displacement, second is the velocity, and here this is the acceleration. So here this is the graphical representation of the displacement, velocity, and the acceleration. So thus, if the mass of the oscillating particle, m is the mass of the oscillating particle, then what it is the kinetic energy. So therefore here, if m is the mass of the oscillating particle, so therefore its kinetic energy what is its kinetic energy? So therefore kinetic energy is equal to 1/2 mx square, 1/2 mx square. Okay, now here we have to give the name of this equation, that is here this is the 1, 2nd, and the 3rd. Okay, so here this is the equation 4. Kinetic energy is equal to 1/2 mx square. So here that is equal to 1/2 m. So x square, here x is equal to, that is a omega cos omega t. Okay, so here we write this x, so that is m a square omega square cos square omega t. Okay, and here when phi is equal to 0, when the phi is equal to 0, and so therefore here this 1/2 m a square omega square, and what is value of the cos square omega t? 1 minus sin square omega t. Okay, and so therefore 1/2 m omega square into a square minus a square sin square omega t. We simplify these equations, and so therefore we obtain 1/2 m omega square into here a square minus x square, a square minus a square sin omega t, and phi is equal to here 0, so that is a x square. Okay, so here this kinetic energy is equal to 1/2 m omega square a square minus x square. So there are the two cases. So case first, here if x is equal to 0, means that is the mean position. So therefore what is kinetic energy? So kinetic energy is equal to 1/2 m omega square a square, and that is equal to maximum. That is the maximum. Okay, and here if x is equal to plus minus a, so that is the extreme position, position. So what is kinetic energy? So kinetic energy is equal to 0. Kinetic energy is equal to 0, and that is the minimum. That is the minimum. Okay, and here let us we find the potential energy of an oscillator. So for that purpose, here what is the potential energy of the oscillator? So here is potential energy. Now here let us find out potential energy. Potential energy of the oscillator. Let us find out the potential energy of the oscillator. And here, if F is equal to minus Kx is the restoring force. Restoring force acting on the particle, and then work done against this force for producing a further displacement dx, and this work done is given as dw, and that is equal to minus f dx, and that is equal to kx dx. That is equal to kx dx, and negative sign shows that the work done work is done on the particle. Work is done on the particle. Okay, and here, so therefore the total work done in order to produce displacement x, total work done in order to produce the displacement x, and here this w is equal to integration dw, and that is equal to 0 to x, here kx dx, and that is equal to 1/2 kx square, 1/2 kx square. Okay, and so here this work, this is the w, this work being done on the oscillator and represents its potential energy, and so therefore here potential energy is equal to 1/2 kx square, and that is equal to 1/2 m omega square x square, 1/2 k square, and that is equal to 1/2 omega 1/2 m omega square x square. Okay, and here this k is equal to m omega square. This is the value of the potential energy, and in the previous discussion, so this is the expression for the kinetic energy. Okay, kinetic energy 1/2 m omega square a square minus x square, and this is the potential energy 1/2 kx square 1/2 m omega square x square. Okay, and now here another case. In this case, first, if x equal to 0, that is mean position, so therefore the potential energy is equal to 0, and that is equal to the minimum. Okay, and the second, if x is equal to plus minus a, and that is the extreme position. That is extreme position, and so therefore here this potential energy is equal to 1/2 m omega square a square, and that is the maximum. That is maximum. Okay, and so therefore when we take the total energy, so total energy is equal to kinetic energy plus potential energy. So here the summation of the kinetic energy and the potential energy. So what is kinetic energy here? 1/2 m omega square a square minus x square plus, what is potential energy? 1/2 m omega square a square. Okay, 1/2 m omega square a square minus x square kinetic energy plus 1/2 m omega square a square potential energy, and so therefore here we obtain this E is equal to 1/2 m omega square a square. Okay, and when we put up the omega is equal to 2 pi nu here, so E is equal to 1/2 m 2 pi nu bracket square a square, 2 pi nu bracket square and the a square, and so therefore these E is equal to 1/2 m 4 pi square nu square a square when we make the square of this. Okay, and so therefore here E is equal to twice pi square m nu square a square. This is the E. Okay, 2 pi square m nu square a square. So here this is the most important relation. Okay, or it is also written as E is equal to 1/2 Ka square. It is also written as 1/2 Ka square. So here this relation here, so when we give the name of the such equations, so this is equation 4, this is the equation 5, then this is the equation 6, equation 6, and here this is the equation 7. This equation is a 7. Okay, so here is equal to 2 pi, and so this relation shows the total energy of the SHM is directly proportional to the square of its frequency and the square of its amplitude. Okay, square of its amplitude, and so therefore here this equation 7 this equation 7 is shows that the total energy of SHM, total energy of SHM is directly proportional to the square of its frequency, square of its frequency, square of its frequency, and the square of the amplitude, and the square of the amplitude, square of the amplitude. Okay, and thus we see that here during the SHM, the total energy of the oscillator alternates between kinetic and potential forms, and in the mean position the energy is entirely kinetic, while in the extreme position the energy is entirely potential. So in any other position the energy is partly kinetic and partly potential, but the total energy is always constant. Okay, and which is shown in the particular figure here. So when we see this figure, so this figure represent as the potential energy and kinetic energy of the SHM versus a displacement, So here this is the displacement versus, that is SHM potential energy, this is the total energy, and this is the displacement. So here we can say that these energy is entirely here, these are kinetic, here this is kinetic energy, and here this is the potential energy. Energy is partly kinetic and the partly potential, but here the total energy is always a constant. So this statement, and this is shown in this that is by the graph, that is potential energy and kinetic energy of the SHM versus a displacement. Okay, so this is the one of the characteristics of the linear SHM, that is the energy of the simple harmonic motion. Okay, so we stop here. Thank you all of you.